Okay, so let's talk about the normal force a little bit more and use a specific example. So in this example, we have a 5 kilogram box sitting on a table, and it's at rest, so it's not moving at all. What's the normal force between the table and the box? So to figure that out, we can draw a free body diagram for the box. So the two forces acting on the box are mg pointing downwards and the normal force pointing upwards. And in this case, the box is not accelerating at all. So we can say the sum of the forces has to equal. If we define the positive direction as up, then when we add up the forces, we get the normal force minus mg equals 0, or the normal force has to equal mg, which in this case is 5 kilograms times 9.8 meters per second squared, which is 49 newtons. Okay, so that was pretty straightforward, but what happens now if someone walks along next to this box, and now they reach out and they push down on the box? It's still on the table, so it's still not accelerating at all. It can't move. But what's going to happen to the normal force? Do you think it's going to be bigger or smaller than it was before? So you can pause it here for a little bit if you want to sit and think about it for a little before I go on. Okay, so to figure this out, we should draw another free body diagram. Now we have gravity pushing downwards. We have the normal force pointing upwards, just like before. But now we have a third force, the force from that person, also pushing down. Okay. So now, when we set up the sum of the forces equaling 0, we have to say the normal force minus mg minus the force of the person pushing down on the box has to equal 0. So now the normal force is going to be mg plus the force from the person. Now, if we don't know how much force the person is pushing down on the box with, we can't give a real number here. We can just say that now the normal force has increased. So the table is kind of springy. The more you push down on it, the more it's going to push back up. And that's why the box isn't accelerating. So we'd say the answer to that question, what happens to the normal force? The normal force increased. Okay, so in part C, we have a similar question, but now the person is pulling up a little bit on the box. So instead of pushing down, maybe there's like a little handle now, and the person grabs onto the handle, and they're pulling up a little bit. What do you think is going to happen to the normal force between the table and box now? And again, I'll give you, if you want to pause right now and think about what happens before I move on, now would be the time to do that. Okay, so let's scroll down and go through what the free body diagram looks like for the box now. So we have gravity pulling down, we have the normal force from the table pushing up, and then now we also have the force from the person pulling up on the block. And again, the block is not accelerating up off of the table, it's still sitting on the table. And so as long as that's true, then the sum of the forces still has to equal 0. And that means the normal force plus the force of the person pulling on it minus mg has to equal 0, or the normal force is equal to mg minus the force of the person pulling. Right? So what we can say now, again, we haven't said how much force the person is pulling with, but when the person is pulling up, that's going to decrease the total amount of normal force from what it was before. So the normal force decreased when the person pulled up on the box. And that's because now the table needs to provide less force to support the weight of the box. So the part of the point of this question is to show you that the normal force can be totally different in different situations. It's always perpendicular, but the magnitude of it really depends on what else is going on in the problem.